Record. All right, cool. So everyone should have just gotten like a little message saying like this session is being recorded, correct? Yeah.
Yes.
Okay, cool. All right, so welcome. This is the review session for COT3100, that is discrete data structures at UF for the Summer C 2022 semester. I have put together a small presentation to go with you guys. That's basically just going to give a summary of all of the big points for Unit 1. That is everything that is on our exam tomorrow morning during class. Before I get into the presentation, a couple of disclaimers. No, I'm not a TA. No, I'm not a professor, which technically means that since I made all these slides, something could be wrong on the slides. If you noticed something is wrong, feel free to point it out because I wouldn't want to purposely mislead everybody, here. So once again, if you notice something is just slightly messed up on a slide, just point it out and I'll fix it on the spot. I'm not going to release the PowerPoint slides publicly until after this. That way, if there are any issues that have to be fixed, I'm not putting out wrong PowerPoint slides. So yeah. So here we have at the very beginning, we have this wonderful meme that I created. It's when the proof is finished, but you're still at like the very first step where someone has said that assume x equals n plus 1 factorial plus 1, and you're just sitting there like, where did that even come from? Because that's a good question. So I'm gonna move on. I gotta actually go to the PowerPoint, hold it, PowerPoint presentation software. And there we go. Okay, cool. So there are basically 4 big topics for this exam. If you haven't noticed that by now, there's the first, which we go over propositional logic. The second, we're going to go over predicate calculus. I put calculus in quotes because it's called predicate calculus, but at least for the scope of this class, you're going to notice there isn't any real calculus. It's more like predicate logic and just looking at symbols and know what they mean. Then there's inference, which has a few more laws and rules that we can once again use for proofs. And then there finally is proofs, which is kind of like putting everything together that we've done in the first 3 sections and actually being able to formulate, take hypotheses in and formulate logical conclusions. So if we go to, let's see, I'm going to mute everyone again. Sorry. There we go. All right. So let's see, hold up. There we go. So once again, so first we have a propositional logic and we're going to start off with like the very basics. So a proposition, guys, is a statement that can be said as either true or false. Notice I have written here that it cannot be a question, it cannot be a command. So if I said like, what is the capital of Florida? That would be a question. That's not a proposition. However, if I were to say the capital of Florida is Tallahassee, that would be a proposition because that has a value that we can say is true. Now, if I were to say, tell me the capital of Florida, that is a command. Therefore, that is not a proposition. Now, finally, if I were to say the capital of Florida is Miami, that would still be a proposition. That would just be a false proposition. So once again, propositions, they can be true or false, but they cannot be anything else. They're not questions, not commands. I have written here, they're oftentimes represented by P, Q, R, and S. Of course, technically, you can use any variable you want. It doesn't really matter. Just know that for exams and everything, if something has one of those letters and it's lowercase, it is probably representing some form of proposition. Then we have negation, which is like the first basic rule of propositions. And something I want you guys to understand is that negation does the exact opposite of whatever is being said. So for example, we have this practice problem here. It says, what is the negation of x is negative? Now, a lot of people, when answering this, they're tempted to say, well, the negation would be that x is positive, right? But that's not entirely the case because think about 0 here. Is it 0 positive? Is 0 negative? No, it's neither. It's a natural number, which you go over more in sets later on, but because it's neither positive or negative, it is still not negative, but it is not positive. Therefore, the answer to that question would not just be to say x is positive, it would be to say x is not negative, or x, if I do right here, there should be like a little answer, x is greater than or equal to 0, right? So once again,
You want to go in? I open the door for you to go in.
let's see, gonna mute again. Let's see. I don't know how to do the like default setting where I just have everyone default muted, but anyways, so yeah, basically if we go to from x is negative, then we're going to say that the opposite or the negation of it is that x is not negative or x is greater than or equal to 0. There are a lot of symbols, and also we're going to go over truth tables. There are so many random symbols that before you come into discrete data structures, you've probably never even seen any of them before. But then after you actually look at them, you're like, okay, that makes sense. So there, yeah, there's the answer for that. X is greater than or equal to 0. And we're going to move on. All right, so here's all these symbols for propositional logic. We're going to go through these. So first of all, anybody in the audience know what the first one is? Yeah, that's a negation. So for example, if we had that in front of like a P or something in front of a proposition, that would mean the negation of P. And I just showed all the answers. We're going to go back. Hold up, guys. Then we have the second one. What is that, guys? And which is called, I mean, I kind of showed it already, so it doesn't really matter, but it's called a conjunction. And then what do we have next after that? An or, which is a disjunction. And then after that, what do we have? Exclusive or, which is just exclusive or, to be honest. And then after that, what do we have? Implication. Dude, I'm so confused. It's turned my biconditional into some form of emoji thing. I didn't even notice this when I was making the PowerPoint presentation, but that's crazy. But anyways, yeah, that's a biconditional statement right there. And then we have logical equivalence. Now, something I want you guys to keep in mind, technically, right? See if I can draw these. Technically have the same meaning. That's something, I'm sorry, my handwriting's terrible, but those can actually be used interchangeably, because if you make a truth table and you look at them, they're going to end up having the same values. So I found out that in some other textbooks, maybe not for this class, in a lot of the areas that we see the triple equal sign, it's actually sometimes referred to, they just use the biconditional operator. But so yeah, then we have all this that does say what it is. Now, once again, a negation we talked about, it's the opposite. A conjunction, what do we need for a conjunction to be true, for example? So if we put a little table, what do we need for it to be true over here for a conjunction? Yeah, both of them would have to be true. So we would need to have true and true, right? For a disjunction, what do we need? We need just one true. So basically we would need true or true would work, true or false would work, or false or true, right? So then we have exclusivity. What is the difference between exclusive or and a normal inclusive or? Right, only one can be true. So basically, with an exclusive or, it's almost the same thing as an or, but instead of having this true or true actually work, it actually wouldn't. So basically, we have true or false, or we would have false or true would work for the exclusive or. What's the implication, guys? Okay, this is something everyone seems to stumble on. Yeah. Right. So basically, if you have P implies Q, right? That would be the same thing as saying either A, P is false, or you would have Q is true, right? Because the reason that works is because think about it. When you have an implication, remember in the truth table, if the left proposition is false, even if the right proposition is true, we still say that that implicates it because we don't really have enough knowledge about the left proposition to say that it doesn't imply it. Whereas if the right proposition is true, that also means that even if the left is false, once again, we implicate it. So what is the only time that we can have an implication where it's actually false? There's only one time. Yes, so it's when the left, if we have, this would actually be false, right? So it would be false if we have the left is a true implying a false for an implication, right? So keep that in mind. And then the biconditional, does anybody know the fancy representation for a biconditional? Yes. Right, so yeah, so biconditional is basically saying P implies Q. Once again, if we had this right here, right? What a biconditional would really be saying is we have P implies Q, and Q implies P. Now, also, while I was looking into this, I found out something somewhat interesting. Notice that a biconditional is actually the negation of an exclusive OR. Because with a biconditional, right, it's either true and true or false and false work. But with an exclusive OR, those are actually the two that don't work. So you can actually do a proof where you can actually probably prove that biconditional and the negation of exclusivity are actually like the same. That's fairly interesting. And logical equivalence, once again, it technically, in a sense, it means the same thing as the biconditional statement. But basically what logical equivalence is saying if you made a truth table, you would get the same true or false values depending as long as you have the same conditions for like whatever propositions you're doing. So we could really write this. We could actually put a logical equivalence symbol right here, right, for these to show that this is the same as this. Hopefully that makes sense to you guys. So now we're going to move on. Propositional logic part 3, guys. All right, so I want to go through the actual process of constructing a truth table because I feel like everyone, when they look at truth tables, they understand it to a basic level, but then when they look at maybe a little bit more complicated proposition, they're 100% sure, okay, how many rows do I have to include? What do I need for how many columns, et cetera. So I want to go over that with you guys real quick. So first of all, you're going to look at the proposition. So I have an example of a proposition. We're saying the entire proposition on the left is logically equivalent to the entire proposition on the right, or rather, hold up, let me get the eraser. That parentheses should be right here. And we're just wondering, like, what is it? Okay. Or is this a true or false statement, right? So in order to construct a truth table, what we're going to have to do is first you want to look at how many columns you're going to have, or rather, or how many rows. It doesn't really matter. I have it actually written as rows first. But so we know that for the rows, if you look, there are a total of 3 variables, or 3 propositions rather. Because there are 3 propositions, what you're going to have to do is you're going to have to take the 2 and you're going to raise it to that power, because that's how many total combinations of true or false we're going to have. Now you're also going to want some form of hetero row. That way, you know what you're actually doing. So basically, the general rule is it's 2 to the power of however many variables you have. But then I always say also add 1 because you're going to have your hetero row. So this is going to be like 9 total rows. But there could be a question where it's like, if it asks like how many rows you might have, the answer might just be 2 to the power of 3. Personally, I would just write 2 to the power of 3 plus a header row, if that makes sense. So then we have the columns. So you're going to need 1 column for every proposition, or like individual proposition or variable you're going to have. And then you're going to need another column for every negation that you have. Now notice there is nothing here that says negation of R, like in this original, statement. So I don't have a column for the negation of R. However, we do have the negation of P and the negation of Q. So that is why those are included there. And then you're going to have to go and you're going to have to break them all up. And you're going to have to break each individual part of the proposition up and say, okay, like we can see that this is part of this right here, right? And then we can see that this is part of this. And then this is like the entire thing over here. So you have to break it up into like subsections when you're looking at this and list every single subsection, yes. We'll get to that when we do a truth table. That's like part of the exercise is trust. Okay. So yeah. So we're actually going to go look at this. I'll show you fancy slide. Neither of these are always true or either false or always false, if that's what you're asking, but they are equivalent, yes. They are indeed equivalent, yes. So we're going to go, let's see if I can click the next slide. All right, we have a fancy truth table here, okay? So what I'm going to do here, and we're going to hope I don't mess up. However, what I'm going to do here is I'm going to start off, we're going to go to P, right? And let me go to red. There we go. We're going to go to P, and you want to go to the first one and say, okay, there's a total of 8, right? Which means that there's going to be 4 times that P can be true, and 4 times it's going to be false, right? There should be 8. Yeah, there is 8. And then after that, I want to go to Q, right? And So once again, there's 4 times each, but notice that we have 3 total variables. So what I'm going to do is I'm going to say there's going to be 2 times that Q and P are both true, and there's going to be 2 times that P and Q are true, false. And then I'm going to just do true, true, false, false again. Once again, technically to make a truth table, you don't have to do this exact order. It's just the way I find it easiest to show off, and like you can do this every time. Like if you did a slightly different order, it would still work out as long as you have all of the combinations. But if you just like memorize this kind of little trick, then it makes it much easier. So then for the third, we're going to have true, false, true, false, true, false, true, false, right? So that brings us to the next part. Now we have to look at, okay, let's do the negation of P and the negation of Q, because this is this is every possible scenario right here of P, Q, and R, okay, guys? So then if we look at the negation of P, we're just going to do the opposite of P. So we know that the first 4 are true. So for this negation, we're going to do first 4 are false. And then true, 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 true. You guys see that? And then for here, for the negation of Q, it's also pretty simple because we can just go and false, false, true, true, false, false, true, true, right? So now it gets a little bit more complicated. So we're doing the negation of P or the negation of Q or R, right? So now when I say that, what do we need to look at? That means what we're really doing here is we're saying that one of these 3, right, is true, because we have the negation of P, we have the negation of Q, and the negation, and just R itself, right? So we can see here, right? And also notice that this is the entirety of our left side. So this is going to be like an important row that we're going to have to compare later as well. So we're going to go here and we're going to go, this is going to be true because we have a true statement right here, an R, and this is going to be false because they're all 3 false. And I believe just the rest of them are true. So, because yeah, we have true there, we have true there, we have true there, true there, true there, and true there. Okay, so you guys see how that works, how I actually got those values. It was just looking at those 3 and making sure at least one of them was true. So next up, let me erase this. And next up, we have P and Q. Now remember that for P and Q, that means that both of them need to be true. And now in this case, we are looking at, that was a terrible picture, but we're looking at these 2. And once again, they both need to be true. So we're going to say P and Q right here is true. And then we're going to have right here is true as well. Now those are the only 2 scenarios where P and Q are both true, which means that everything else is just going to be false. So now, finally, we're going to have P and Q implies R. Now, remember that I talked about earlier. So first of all, we are actually now looking at this right here, and we're looking at R, okay? I reminded you guys earlier that when you have a false proposition, when something is false, the left proposition is false. When you're implying something, it is always true. So we can actually look at this table and we can write truths for every single one down, right, starting from there, because they're all false. The left side is false. So now we have these 2 where they're true. Now, in order for a true proposition to imply something that is to be implied as true, we need it to be true implies true. True implies false, remember, is false, right? So what we get here is we're looking at P and Q. We know that this is true and this is true. So we're going to look at R over here. We see that in this scenario, it is false, and in this scenario, it is true. So true implies false would give us a false result here, and true implies true would give us a true result here. Now, finally, we've completed the entire table. And if we look at this table, now if we compare this row, which is literally our left side, and we compare this row, which is literally our right side, what is the conclusion here, guys? Are they logically equivalent? Yeah, they are, because if you look, they have in the same positions, they always have the same truth or false values. So does that was I tried to make a more complicated example than just showing like a basic 2 by 2 truth table or something. Hopefully that helps you guys if we get some form of question where there is a more complicated truth table, like you understand kind of the actual process of setting up a table for that. And on top of that, because this is going to be recorded, if you have any, questions or like you forget something, then you can always go back to the recording and watch. So we're going to move on from that now, though. How does false imply true? That is the definition of an implication. I guess because the right side is true. So it's basically saying, we could say, let me think, the sky is blue. That's true, right? So then we could say, if somebody comes up and they're like, I don't know what color the sky is, but we know the statement the sky is blue is true anyways. We can say that it doesn't matter what color they think the sky is. It's going to be blue. It's going to be implied true. Yeah. So I'm going to move on now. Shri trolling in the chat with the questions. All right. So there's the answer key. It's the same exact thing that we just went through. Just, that was in the unfortunate scenario that I made a mistake. I wanted to have the answer key up just in case. So yeah. So next up, oh boy, you guys know these. Well, maybe you don't know them. This is some stuff that I recommend. Remember, we're allowed to have a formula sheet that you're making on your own. I recommend putting a lot of this stuff on your formula sheet if it's stuff that you don't commonly remember. But we're just going to go through each one of these laws. I'm going to sit down real quick because this is going to take a fat moment. So let's see. We have the identity laws. Now notice the identity laws, how do these work? If we have P and true, it's just going to be P, because if P is false, we have a false and true, it's going to go to false. If we have a true, it's going to be true and true, it's just going to go to true. So once again, you can actually make a tiny little table for that, and you can technically prove that. But you can also just say it's an identity law. It's something that's so basic that like we have an actual law for it, and you wouldn't have to actually draw a truth table for that. With that being said, P or false works the same way. Notice that if we have something ORed with false, it's just going to depend on that original proposition. If we have true or false, it's going to be true. If we have false or false, it's going to be false. Now, the domination laws are kind of the opposite. If we have something ORed with true, then since only one of them has to be true, it's going to be true no matter what. And if we have something ANDed with false, since both of them have to be true for it to be true, it's going to be false no matter what. Then we have the idempotent laws, or however you pronounce that. Note that P or P is the same thing as P, and P is also the same thing as P. There's no reason to write the same proposition ANDed or ORed with itself, because we know that they mean the same thing. You might have to do some, associative property stuff to switch these around and then maybe take out certain propositions when you're doing a simplification problem. Then we have the double negation law, which is actually part of De Morgan's law, which we'll get to in a bit. Basically, what that's saying, though, is the opposite of an opposite is the original. Hopefully that makes sense. The commutative laws, I don't know if you guys remember when you were in like elementary school and you learned like the commutative property of multiplication, but that's just basically saying you can switch two numbers being multiplied and they're still going to multiply to the same thing. It is the commutative laws are basically saying the same thing here. We can switch with if two things are ORed or ANDed, we can switch where they're at and use that. That is very substantial to know for implication evidence, which we'll get to later. Then we have the associative laws, which is basically you can switch parentheses around if everything is the same sign. So if we have P or Q or R, it doesn't matter where we put the parentheses, and same thing if we have P and Q and R. But notice that that does not mean that we can do that if they are different signs. So if we had like P or Q and R, since we have an or and an and there, we would not be able to use these associative laws, because that would actually have a completely different meaning. So keep that in mind. Then we have the distributive laws. Once again, so this is just saying, okay, this is how it works when you do have different signs. So notice in the distributive laws, like right here, hold up, I just went back. No, oh wait, that's actually forward, crazy. Okay, so notice, let me get my pen on. Notice in the distributive laws, you have opposite signs, guys, and then here you have the same signs. So that's like the biggest difference between the associative and the distributive laws. Now, if you have P or Q and R, that's basically saying you either have P or Q well, you have P or Q and P and R, or R, and P or R, because think about it. This means that, you either have P or, well, you have Q and R. So either way, we're going to have, if we take this Q and R, we're going to have one of the two, if that makes sense. Then we have another distributive law, once again, that's going from opposite to opposite. This is going from and to or. So keep that in mind. Then we have De Morgan's law. De Morgan's law is like super duper essential. It's one of the laws that they just expect you to memorize, really. And like it should be something that when you look at one proposition and it says do De Morgan's law, you should be able to do it like ASAP off the top of your head. But basically what it's saying is when you have a compound proposition, that is a proposition with multiple smaller propositions, if you have an and or an or in that, when you negate everything, you're not just putting negations in front of each individual proposition. You also need to switch the sign of all the ands and ors. So for example, you can see in the law right here, we have the negation of P and Q is not the negation of P and the negation of Q. It is the negation of P or the negation of Q, logically. And the same thing upholds for if we started with the or and went to the and. Then we have absorption laws. So if we look at these, we have P or P and Q is going to be the same as just P, because think about it, right? If P is false, right? Then basically, if P is false, what's going to happen is this is going to turn false. And if P is false, since this is an and, this is also going to be false, right? So like either way, we're going to have two falses. Whereas if we were to look at the same thing, P be true, well then, because this is an or right here, if P is true, the entire thing's true. So that is why those absorption laws work. And then finally, we have the basic negation laws, which are basically saying if you have P or the negation of P, well, that means you have every single scenario. So it's going to have to be true. And vice versa, if you have P and the negation of P, well, that's going to be mutually exclusive events happening at the same time. That is not possible, and therefore it is false. So hopefully that helps you guys. So then we have a ton of logical equivalences. I'm not going to go through every single one of these because it takes so long, but yeah, what's up? So for absorption, right, if we have P or P and Q, and you look at it, right, it's just going to be equal to P, because if P is false, then you can see that the left side is going to be false, but then the right side's also going to be false because we have P ANDed with Q, which means P must be true for that side to be true. So because it's false, they're both going to be false. Meanwhile, if P is true, because in the middle here, like in the middle right here, we have an or. If P is true, that just means the entire thing is going to be true, which once again, if you were to write a truth table of some sort or something, that will show you that this law holds up. They're logically equivalent. Yeah. So once again, I'm not going to go through every single one on table 7 and table 8. I would know these. They make sense when you look through them all. But the biggest one I want to go through right here is this right here. This is called implication evidence. And it is what I mentioned earlier. It's the law, I guess you could say. Once again, it's technically not a law, but it can be really easily proven by a truth table. But it is the reasoning you can use to basically turn a implication symbol into just negations and ors and ands and all that stuff. So know that P implies Q is logically equivalent to the negation of P or Q. That is extremely important, okay? So now I have an extremely simple proof here using the logic rules. Now notice this is the same thing that we did earlier with the truth table, but now we're using logic rules to basically prove that one can be simplified to be the other, right? So we have the negation, once again, on the left side, we have the negation of P or the negation of Q or R, and we're trying to figure out, is this logically equivalent to P and Q implies R? So we have the premise right there. That's what we're starting off with, and we're going to try to turn it into the right side. So we're going to start with the left side. We're going to do a direct proof to try to turn it into the right side. So we're going to use De Morgan's law. Now, De Morgan's law works both ways, right? Remember, De Morgan's law is like, if we go from, or no, rather, not that. Let's see. Now, De Morgan's law, what it says is if we take the negation of P and Q it says that this is actually equal to the negation of P or the negation of Q. And this is how I actually came up with this problem in the first place, because I wanted to I obviously wanted to make a problem that was true so I could run through the entire simulation. This is how I started off with making this problem. I looked at this and I was like, okay, I can change this up and do some manipulations and make this problem. But anyway, so notice that if we have this negation equals that, we can do that the opposite way, and it's still De Morgan's law. So basically what we can say is this actually means this. So that's exactly what we're doing in this step right here. We're using De Morgan's law with these two right here and saying that this is the same thing as the negation of P and Q or R. Now notice then we have implication evidence, which once again I said can be proven by a truth table in itself, but we have implication evidence. We have the negation of an entire proposition or a proposition, right? So what that means is that this is the same thing as saying this proposition implies this. So once again, keep that in mind. So then that is our conclusion right there, is that these two are, yes, logically equivalent. That lines up with our truth table example earlier, where we did show that, yes, in every single case that is possible, these produce the same result, okay? So now we get to predicate calculus, and believe it or not, propositional logic was a pretty long section. So, oops, I pressed a button, but that's a pretty long section. So we're actually pretty far along the way, don't worry. So predicate calculus sounds super fancy. When I first got to this section, I was like, dude, let's go. We're doing calculus and discrete. And then I got to this section and I was like, there's zero calculus, or at least not what we're learning uses any calculus. I guess it's technically logical calculus or something, but okay. So I looked at this. All right, basically, long story short, guys, there are three fancy symbols that you need to know the definitions of. The first is the universal quantifier, which I found it makes the most sense to just replace every time you see this upside down A with for all. Like if you just say for all and then you say it in English, it makes a lot of sense. Then you have the existential quantifier, which is the same thing as saying, also backwards E type thing. Same thing as saying there's at least one. Notice when I say at least one, I mean at least one. It can be one, it can be more than one, it doesn't matter. It just cannot be less than one or zero or whatever. There is not a case. And then finally, we have the uniqueness quantifier, which is just the backwards E with a little exclamation point, as you can see right there. And that is saying there is exactly one. Meaning, if we wanted to prove that wrong, what are the two ways we could prove the uniqueness quantifier wrong? There's two ways to say that there's not exactly one. Yes. Yeah, you find two answers. If you find two that work, then the uniqueness quantifier no longer holds true, and there's one other way. Yes. Yeah, you can prove, and I think that's what Holly was about to say as well. You can prove somehow that there are no cases. That is, so you either prove there are none, or you prove there are more than one for the uniqueness. So once again, let's say we have an example here, guys. We define a variable domain X as X represents a U of student. And then we're going to define a function. This is the steps. Whenever you have a predicate calculus problem, you're going to first need to define some variables. After you define some variables, you're probably going to need to define some functions. And then you're going to have to read it in plain English using basically these statements here. That makes sense. So once again, X represents a U of student. And let's say d of X is a function that says X is in COT3100. That could be an example. You could also make this a multivariable function, and you could say y is there, and you could say y is all the courses at UF, which will get us right into, I think, our next point, right? So yeah, so now I have two examples for this predicate calculus stuff just to go through. The first I wrote, we're going to use predicate calculus to logically represent, that means not in plain English, represent there is a student at UF enrolled in COT3100 and in COP3503C, which means that they're enrolled in both classes at the same time, right? So what I would start off doing, I told you guys, we got to start off by defining some variables. So we're going to define X as a UF student, and we're going to define Y as a course at UF. So the domain or the universe of discourse or whatever for X, which is actually that's stuff that we'll get to next chapter, the universe of discourse, fancy vocab term. Basically, the domain for X is all UF students, and the domain for Y is all the courses at UF. So then after I said we define a variable, we define a function or multiple functions, depending on what we're doing. We're going to define the function cxy as the proposition X is enrolled in course Y, okay? So now, how did I write this right here? Well, once again, the final step is going to be to use plain English to figure out how to write this. So if we go back a slide, right, we have there's at least one, and there is a student means the same thing as there is at least one. There is a. It's not there is exactly one student in this case. I meant like there is at least one student. If it said there's exactly one student or implied that somehow, then obviously we would have to use the uniqueness quantifier. But so anyways, we have there is a X, and what is X? X is a UF student. So this entire thing says there is a student where they are both, and then we have our function X is enrolled in course Y. So there is a student where that student is enrolled in COT3100, and that student, we have that same function again, and that student is enrolled in COP3503C. So does that example kind of make sense to you guys? Hopefully you can see how you can just use these definitions to put together these statements, right? So now I have another example, and this example gets a little bit more complicated, but because there are kind of two answers, because I wanted to go through also negation of predicate calculus, because you probably will need to know how to negate predicate statements. So we have there is not a student enrolled in every course at UF. So what does this mean? This means that there's no student who's taking every course at the same time, right? What we're going to say for this, think about this in English. We're going to say there is not a student, which means there is not at least one student, right? So that is why we get the, you can see here we have the negation. And then how many courses are we talking about? We're talking about every single course. So that is why we have the upside down A, which is the universal quantifier, which means, so now we have there's not a student who for every course is enrolled in every course, basically. So this is what this statement is saying, is there is not a student who's enrolled in every course, that first answer. Now notice, then we have the second answer there, right? Whenever you negate something, let me go to the side, right? We have this negation. You can see that says negation backwards EX, upside down AY, and then C of XY. When you negate something for predicate calculus, you're going to have to change the backward E's to upside down A's, and you're going to have to change the upside down A's to backwards E's. So we're going to start by saying, this is the same thing as saying for all X, basically negation all Y, C of XY. And then, so do you guys see how I moved it in one at first? I didn't just immediately do everything. I went one step at a time. We moved the negation in one step and flipped. And then after that, we can move it in one more time to finish it off. We get for all X, there is a Y where C of XY is not true. So now let's really think about this, and this is the answer we have right here, right? Let's really think about what this is saying. I have it written there because it is a little bit hard to think about logically. But basically what this is saying is for every student, there is at least one class that they are not taking. So they mean the same thing. You can say there is not a student who is in every class, or you can say for every student, there is at least one class they're not taking. They mean the same thing, but they're just two different ways in English to say it. And as you can see, they have two corresponding predicate calculus logic examples to write them out. Okay. Now, finally, I have one note. You can thank Eli for telling me to add this in the slides. Basically, if we look at these predicate calculus stuff, and we have something Y and something X, and we take them and we swap them. So, for example, if you look at this example, this is the same thing as this, but the only difference is we have taken X and Y and we've flipped their positions. This is not the same thing. This is, if we read this out, we know that Y is in the position of the UF courses, and X is in the position of the students. So what this is actually saying is there is a course where for all students, there is nobody taking that course. So basically what this is saying is there's a course that nobody's taking. Now, realistically, would this be a true proposition, would you guys say? Is there a course nobody is enrolled in right now? Well, the answer to that would actually be true because there are courses that are not being offered right now that still exist. So that would be a true proposition, actually. Yeah, I don't think you'll need to know that for the exam, but that's just, there are lots of courses that are not being offered. Yeah.
Okay, so if you have like negation, I'm just doing this. If you have negation upside down AX, and then backwards EY, and then you're like CXY. I know how you negate that, but let's say the negation, like in this example, where the negation is in between the two,
Yeah.
then you don't negate the one in front of it.
So like if you're saying if you start off with this, basically, what happens? Like, how do you do this?
Yeah, so it just goes to that.
Yeah, it would just go to the bottom one, or you could even.
You only negate the stuff behind the negation.
Right, you could even actually put this up front still and switch the X as well. Like you can say that this is equal to this, where we move it in and switch it, or we could actually move it out and say this is also equal to, we take it outside and we do this. Like we take it outside, but you could do either one. It goes both ways. Yeah. Like just think about it like if you can go forwards, you can also go backwards. It's kind of like the logic. If you can multiply by 3, you can multiply by 3 and divide by 3, and you'll still get the same thing, right? So yeah, hopefully that makes sense. If you want, I can like Discord message you later, like more explanations. Yeah. All right, inference. Inference is really predicate calculus part 2, but it's still its own section for whatever reason. But so yeah, now we have inference and we have all these definitions that I have a feeling we're going to have to know for the exam. So I wrote them all out. These are definitions I very, very highly recommend you put on your reference sheets and just have them in their own like area basically, because then if you see something like, oh, match these definitions, or what does this mean, or something along those lines, you can just real quick go to the one section of your reference sheet that you wrote it, and you have all of them right there. Okay. So we have the rules of inference, which what this really just says, this is not a technical definition. Whenever you think of rules of inference, you're going to think of what are we using to actually quote unquote draw conclusions? What are we using to say something is true or false? Then we have a theorem. A theorem is just something that we can prove to be true. And then we have a conjecture. Imagine a conjecture is just an unproven theorem, basically. What? Yes.
If you have a theorem that, if you have a proposition that you're trying to prove true, but it's false, is it still a theorem?
You find out that it's false. No, it's not a theorem. If you find out it's false, it is not a theorem. The theorem is true.
So like a theorem is like a scientific theory. I think of it like
Yes. Yes. If you prove something false, it is no longer a theorem. It's a conjecture. Now, if it is a conjecture, though, keep in mind, like conjectures are things that we're assuming to be true, but we don't actually know. So it's like, maybe let's say you have like a professor or something who's doing some research, right? And he just has like a feeling something is true. And now he wants to go do research. He says, oh, I believe this relationship exists. Maybe it does, maybe it doesn't. That would be a conjecture. If he goes and he does the research and he proves it true, that could become a theorem. If he goes and does the research and he finds out that it's not actually the case, his research shows that it does not work, then it would just be nothing. It would just be a false. There's just a hypothesis that, yeah, that ended up being false. Yeah. So then we have a proof. A proof is basically you showing that something is true through laws and like the stuff that we've already established. Then we have an axiom, which is just a fact. I think in the like RE or something, you have to like put in axiom, but then it also says you can put in like result or fact as the same thing. So just think of an axiom as a fact. Then we have a lemma and a corollary. I don't know, however you pronounce that. So once again, this is like, they're really similar. And I was sitting there like, what's the actual difference between these two? Basically, a lemma is an actual theorem. So you could say like, let's say we have like P implies Q. And in a corollary, we could say that because P implies Q, like we know Q, that would be kind of an example of the difference between lemma and a corollary. The lemma is the theorem used. The corollary is what we're actually concluding from that theorem. And they're usually like smaller than other things. More definitions, guys. Okay, I'll give you guys the option. Do you want me to go through all these, or do you what? Oh my god. Okay. All right. We can go through. Okay, so we have modus ponens and modus tollens. So what I want to point out here for modus ponens and modus tollens is that look at what we're being given, right? In modus ponens, what we're being given is we're being given P. And what is P? P is the left side, right? And modus tollens, we're being given Q, and Q is the right side. So what we're really figuring out here, and once again, if we go to our implication evidence, right, we know that this, right? What we're really saying here is we know that yeah, that is pretty much the case. You know, I don't think I added any slides for contrapositive, converse, and inverse, but we can go over those anyways, because like they're so good to know. The three dots mean therefore. Also, funnily enough, I was looking this up on Wikipedia. Apparently, whatever you do on your exams, if you're writing the three dots, make sure you do it like that. Do not do it like this, because this means because, and this means therefore. So they actually mean different things. So if you accidentally write this dots, you're actually wrong, just so you guys know. Yeah, I just found that out while making this presentation, because in order to make this, like there's like all the fancy symbols and stuff, right? So I had to like go to the Wikipedia page of symbols and use copy and paste. And I saw that and I was like, yeah, that's kind of crazy. That's a bowling ball. You're correct, Logan. That is indeed a bowling ball right there. So yeah. Let's see. So once again, the big difference. Notice we are given information about the left in modus ponens, and we're told the left is true. And in modus tollens, we're given information about the right, and we're told right is false, right? These are all tautologies. Yes, you can prove all of these, or you can just not prove them and you can use them in your proofs. Like, why would you prove them if we're already given them as laws, you know? Now we have hypothetical syllogism. That is a fancy way of saying if P implies Q and Q implies R, we know that P implies R. Think about it for a second. If it's raining, and I don't know. Well, actually, we'll get to examples of this in a second. So I'm not going to go super far in depth. Now we have disjunctive syllogism. We know that what this is really saying is if we know either situation A or situation B is true, and we know situation B or situation A is false, we know the other is true. Like if we know it's an or and we know that or evaluates to true, it's just saying we need at least one of them to be true. So if we know the one that's false, we know that the other one's true. And all of these that we've talked about so far, we will get into, have kind of opposites. They can all similar to fallacies. They're very similar. They sound very similar to a lot of fallacies that people make. And we'll go through those fallacies, but they're not the same, okay? Then we have addition. If we have P implies P, if we know P, right, then we know, if we know P is true, and we have a statement that's P or Q, because P is true, that's the same thing as saying true or P or Q, which, or rather, that is the same thing as saying, if we know P is true, then we have true or Q, which would mean that's true, and if we know P, so that's why we know. Hold on. Explanation. Basically, P must be true. We don't know anything if P is false in this case. That's what I'm trying to say. Implication. Remember that is basically saying, right, so if P is false, yes, that would still be true. Yes, if P was false. not by this law, though. This is saying P implies P or Q, because think about it, right? If P is false, right, then what's going to happen is, yes, this is always going to be true. Now, if P is true, then what's going to happen is P or Q is also going to be true because P is true and it's an or statement. So it's going to be true to true. Now, if P is false, right? Basically, yeah, if P is false, but Q is true, false to true still evaluates to true, hence why this is a tautology, no matter what. This is, so like if P was false, right? We do not know that P or Q is true. Because if you think about this, right? If P is false, then we have a false or Q, and then it's dependent on Q. The actual statement is dependent on Q, because that is another law that we have. It's like a few slides ago. So we have P and Q. If we know that P and Q, we can basically simplify that with simplification and say that we know P is true and we know Q is true. So we can basically take those statements and make them their own separate statements. That's what simplification is doing. Conjunction is basically the opposite of simplification. It's just saying that if we know P is true and we know Q is true, we can also say P and Q is true. And then we have resolution, which is a little bit more complicated. It's, look, if we have P or Q and we have not P or R, right? Now, here's the thing. This means, right? So P or not P, right? Like to be or not to be, I don't know. Like we know that one of those is true, right? So because we know that at least one of those is true, that's why we know that either that for this entire statement, I want to erase that and draw a little smaller. That's why we know that for this entire statement to be true, we know that at least one of Q or R needs to be true. That is a good, actually, that's a good way to look at these weird rules, how they're written. It's basically like if we take like this one right here, we are assuming this is true. And it is assuming this is true, we know that this also has to be true. That makes sense. That is how to read these. So then, let's see, that's basically all those laws. Yeah.
Is this like the little brackets ever change anything? Because I think that when the brackets around individual stuff.
Wait, so you're saying the brackets around a disjunction,
No.
a conjunction? Like which law are you referring to? Oh, right here. Oh, so you're saying P and Q implies P and Q.
But like the brackets, do they do anything?
Are you saying could you remove this, like these parentheses?
Well, obviously,
Yeah.
but like, do they change?
It's really just trying to say the reason that there are these parentheses here is trying to say that you were given these two hypotheses separately and not at the same time. That's the reason they're there. It's to symbolize that you're being given them, like it's not like you got one hypothesis that says P and Q is true. It's that maybe you have a few hypotheses, and maybe with one set of hypotheses you proved P is true, and then after that with another set of hypotheses you proved Q is true. This is saying you can then, because you know P and Q is true, you can then officially say P and Q. So what this is symbolizing, these brackets here, what they're symbolizing is the way that you found those, the way that you concluded those are true, are two separate, like independent ways. Yeah. Okay. Gonna move on. Part 3, let's go. Okay, so we're going to talk about the oh wait, I don't want to skip that though, because here's the thing. I just remembered, I still have to go over this stuff over here. I'm going to erase this here so you guys can actually see. And we have the rules of inference. So, okay guys, biggest, easiest way to memorize these. Notice, universal means it's going to have to do with everything. Existential means it's going to have to be dealing with, that's such a bad E, but it's going to have to be dealing with at least one thing.
Wow.
Bro, you got the entire chat laughing. Sheesh. But anyways, the entire room's blowing up. But anyways, so then we have what we really have is the instantiations. They're saying based on the fact that we know that for all x's, or there is an x, right? We can then provide at least one specific example if it's x essential, or we can take any example and just say that it's true for the instantiations. Now, what the generalizations are saying is the exact opposite. For example, if we know at least one condition is true, then we know that we can say there is an x where the proposition is true, right? If we find one specific element. On the other hand, now everyone's like, what does arbitrary means? What does arbitrary mean? Because you can see it says P of C for arbitrary C. This means arbitrary means that whatever C you pick, it doesn't matter. So like, that's really what that's saying is if you find out that no matter what, maybe you're doing something with numbers, if you find out that whatever number you pick, you're always going to get the same conclusion, then you can conclude that it's always going to work for all x, P of x in that case. So yeah, those are those. Once again, just the trick is to try to remember that they're basically opposites of each other in like every way.
Actually, I have a question about that.
Yeah, what's up?
Does that mean that like say for example, I pick like a random number from like a set and I find out that P of x for that specific number is true. Does that mean that the whole set is true?
So if you pick one specific number, right? That is not considered arbitrary. So that would not prove like the upside down A x P of x. It would not be a universal generalization. However, if you pick a random, once again, if you pick a random specific number, that would be an x essential generalization. So that would prove that there is at least one. Now, when I say you can pick an arbitrary number, it's you're proving it in some way where maybe you don't pick a specific number, maybe you pick a variable and you show that based on some definition that there is no way for the variable to not make it true. That would be how you would do a universal generalization. It's not just like you pick one number and then you can say like, oh, for this set of numbers. Now, I guess you could say, right, if you went through and you decided to pick, okay, I'm going to pick one, right? You plug in one to a function. Then technically you could say that if your set is just one, then yeah. Or if your universe of discourse is just one, then yeah, for all x P of x, because that is your entire universe of discourse. However, that's not very useful. So yeah. Or like, once again, if you pick like 1, 2, 3, 4, you plug 1, 2, 3, 4 in and they all work, you could say, okay, if my domain or if my universe of discourse is 1, 2, 3, or 4, then yeah, for all x P of x, but you aren't going to be able to do that for like every single one. If you expand your universe of discourse, then it's not going to work. Does that make sense?
Kind of. Like I'm still kind of confused on like what exactly like universal generalization means. I get it that like I'm confused on like the definition, you know what I mean?
Yeah,
like,
so you're confused on like what arbitrary really truly means. Is that what you're saying?
No, I'm confused on like what exactly means if we pick an arbitrary C. Like looking what.
So it basically means that no matter what C you pick, it's not going to matter. It's going to have the same results. Once again, the easiest way to prove this is to make C like a variable of some form and maybe mathematically prove that no matter what variable. So for example, let's say we did a proof, right? And we got we said, let's say during our proof, we said K is an integer, a positive, and we'll just say K is an integer, right? And then in a proof, we somewhere got like 2K plus, I don't know, 3 as a thing, right? Now notice that for K, right? No matter what we put in the K, it doesn't matter what value it is. It could be any value, arbitrary, as long as it's an integer, because that's our universe of discourse, right? This is always going to be even because it has this 2 right next to it. If we plug in an odd number, such as 5 plus 3, we're going to get 16. If we plug in an even number, 4 plus 3, we're going to get 7 times 2 is 14. It's always going to be even. If we plug in 0, we're going to get 0 plus 3, which is 6. notice it's always going to be even. It does not matter which number we plug in. K is an arbitrary value C. What was that? I have a question from the audience. Was that Stephen Miller talking?
Why?
I don't know. Like somebody just wanted to know.
Wait, what?
They said they knew. The person in the audience said they always can recognize you because you have a cat face for your Zoom profile picture in programming too.
You want my phone number or something or what? I don't know what you want.
We can also draw universal generalization by saying that the square of any number is greater than or equal to 0, right? That's the only thing you want.
The square, yeah. So like, what Skylar just said was like another example of a universal generalization is n squared is greater than or equal to 0, right? Because we know that no matter what number we put into n, like the smallest thing we can have is 0 squared, which is equal to 0. But like even if we put in like a negative number, like -1, we're still going to get 1, which is greater than or equal to 0. Checks out, right? So like that's like another example of a universal generalization that we could say. See, notice when we're doing these generalizations, though, we're not actually putting in specific numbers. We're just saying that no matter what we put in this, it's going to be true. Does that kind of make sense? Who's the person who called for me? Miley. Exposed.
Can I get your number though?
That's not me.
Wait. That was some random guy who just said, "Can I get your number?" to make you think it was him asking. So these,
Nah, bro, give me your number.
They're great. Too big brain. All right. Anyways, we're moving on, guys. All right. So now we got fallacies. How many slides we got after this? Let's take a look. We got proofs part 1, proofs part 2, and that's it. Okay, cool. We're almost done with these slides. And then I can go over converse and inverse and contrapositive. Yes, Raj. Yeah. And questions. Of course, there's no guarantee if you give me like specific questions, I can like answer everything, but we'll figure it out. So of inference part 3, right? So there are 3 main fallacies, guys. We have affirming the conclusion. Now, remember what this is saying. If we know that Q is true, right? AKA we know oh no, I opened up Microsoft whiteboard. What is this? Decline. Let's just like close that out. There we go. All right, so if we know that Q is true, and we know that P implies Q, then we cannot conclude that P is also true. Because remember, like P could be false, and no matter what, P implies Q is going to be true. So just because we know that that Q is true, we cannot say it. Now, what this is really saying, if we take the eraser here, how we would represent this. So we know that P implies Q, and we know Q, therefore, did I use the right therefore? No clue. But remember to know that for the awesome. Remember to know that for the exam, that therefore and because are different things. Write that down on your like formula sheet. But anyways, if we know that P implies Q and Q, then we can say this is what this is saying is that we can say P, right? But that's just not true. It does not work. Okay. So then we have denying the hypothesis. Now, if we go through this again, well, what it's saying is if we know that P implies Q, and we know the negation of P, then therefore the negation of Q. However, this does not work once again, because once again, if the negation of P is true, or rather if P is false, no matter what, its implication is going to be true, even if Q is false. So that once again is a fallacy that you cannot use. And then finally, we have begging the question or circular reasoning. So it is basically saying, I know this, I know fact A, therefore fact A exists. Or rather, a more common version of this is, I know fact A, therefore I know the double negation of A. Like, that doesn't actually tell us anything, right? So like, if we look at this example, right? I am the best because everyone is worse than me, okay? Like, that doesn't make sense. That's not a legitimate reason for you to be the best. Like, you can't say that you're the best just because everyone's worse. Like, that's begging the question, okay? Maybe you say you're the best because, I don't know, you have some way to prove you're the best. I don't know, maybe you're the best runner at UF because you have the best time in I don't know, some like 400-meter dash or something. Okay, that's a way that you could, that's a legitimate reason you could say I am the best at running. But you cannot say I am the best at running because nobody is better than me at running. That wouldn't make sense. All right, so then finally we have proofs. I have every single type of proof listed out here. And I'm hoping that if we go through all of these and we review them, maybe you can start to immediately think of these types of proofs when we get them on the exam. So we have a direct proof. So what we're going to do is we're going to assume that the left proposition is true, and we're going to show that the right proposition must also be true, if that is true. And remember that if the left proposition is true in an implication, then in order for it to be the entire proposition to be true, what do we need here? True, right? So we need true here. That's what that's saying. And we're gonna, so therefore we're going to prove that. Because if we had false there, then this would not be true, it would be false. So then we have the contraposition or contrapositive. I wrote that wrong. It's not contraposition, it's contrapositive. No, I can't actually. No, I don't want to exit the PowerPoint, but let's see. Might have to close out the PowerPoint and go back in. I did not mean to click escape. I'm going to keep all of this. Yeah, exit the PowerPoint. Okay, don't worry, we got it up. So we're going to go from here. We're going to go from current slide. Then we're going to have to go back to the Zoom. And we're going to have to go to display settings. And we're going to have to swap. And then we're going back to the Zoom. And we're going to go share screen and OK. And then we're going to go to the PowerPoint. Okay, cool. We're back up and running. Okay. So now what I was saying was, now this should be contrapositive. I don't know why I wrote contraposition. I mean, I guess technically you could, in a sense, say that it is a contraposition. But anyways, I'll update that when I post the slides. But what we're going to say is, now what we know, we can actually prove this in some form of logic table, or we could prove this in a logical proof. Basically, if we know that P contraposition, I've already stated what it means. What do you mean? Contrapositive, yes, I will have to change this to contrapositive. But if what it's really saying is that we have P implies Q, right? This is logically equivalent as saying not Q implies not P. All right, so that's a good question. So anyways, what we have here is the negation of Q implies the negation of P. These are two equivalent, logically equivalent statements, right? So what that means is if we can prove that that Q is false, we can basically, or rather, if we assume Q is false and we can prove that P must also be false, that means we can say that the entire, we can say that the entire statement is false, or true, actually, rather. If we can, yeah. So if we assume the negation of Q, aka the negation of the right proposition, and we can prove that the left proposition is also false, then we can say that the entire thing's true. That's what the contrapositive is saying. Then we have vacuous. So notice for vacuous, right? Remember when I was talking about implication evidence earlier, we talked about how no matter what, if the left proposition is false, the entire thing must be true, right? So basically what we're doing is we're taking Q and we're saying we're just not even going to care what Q is. We're just going to prove that P is always false. If we can prove that the left proposition P is always false. No matter what, we know that it doesn't matter if Q is true, false, whatever, it's going to be true, the entire implication. And trivial is basically saying the opposite, right? If we can show that Q, the right side, is true, once again, it doesn't matter what P is, P could be false or true, and we can say that the entire thing is true, the entire proposition, compound proposition. So then, after that, we have a proof by contradiction. Now, a lot of people are like, what is the difference between like a contradiction and a contrapositive? The difference is that basically you're assuming the entire proposition is false. So in this case, it would be we're assuming P and Q are false. We're rather assuming the negation of P and Q, basically, or whatever the entire thing is. Or rather, it would be, we could say negation P implies Q. We assume this, right? And once again, we could use implication evidence to basically write this more formally with just ands and ors. And then we are going to force a situation that we show that having this creates some form of contradiction. Now, what's a contradiction? Contradiction is when you have one proposition anded with the same proposition but the negation, two mutually exclusive events. What this means is that they cannot happen at the same time. So to have them anded at the same time would not make sense. Does that make sense? Hopefully that kind of clicks in y'all's heads. That's the whole point of a contradiction. So these first five are like the first five basic ones. They're the ones that are part of like 1.7, but then we get to a little bit more abstract proofs. Yes.
If I factored into that not signing difference, it just be not key.
So here's how you do that. Miley is asking if we factor this in, how would we do this? So what will we do, right? We get this. We're going to use implication evidence first. So that means that this is the, well, like, hold up, that's like really close. What we would actually get, before we even do the negation, let's do inside the parentheses. Let's turn it to ands and ors and stuff. So we're going to use implication evidence. We're going to say that this is the same as not P or Q, right? And then after that, we'll use De Morgan's law to say that this means P and not Q. There you go. That's how you would like technically do that. Well, let's see, right? So we could say that yeah, no, you can't just like, I don't think you can just factor it in. Unless, let me try it real quick. I can do it right here. So if we did not P, let's see if this turns out to be a tautology. I don't. So then what this would mean is that we would have P or not Q, which let's see P. Yeah, that is wrong. So yeah, you cannot just like real quick. This does not work. You cannot do that. Yeah. Let's see. So we have proofs part 2. Now we have a second set of types of proofs. These proofs are all a little bit more abstract. So the equivalence proof. Equivalence proof is a fancy word for saying show that they are biconditional. You are basically going back to our definition of what biconditional really is. We're showing that P implies Q and Q implies P. Because remember, what did I say to you guys earlier, like at the very beginning? What did I say biconditional really was? What was it kind of logically equivalent to? Well, I just said the answer. It's logically equivalent to logical equivalence. So if you can prove this, you can prove that two things are logically equivalent. Then you have a proof by exhaustion. So this is, let's say you have a domain. It's like in the problem, it says you want to do like all integers. So let's see, let's say we had all positive integers greater, or rather, let me go to eraser. We have all positive integers less than 4, right? Now, what would this actually be for our set? Like what numbers would be included in this? So like keep in mind it's positive integers. Sorry, I don't know if you saw that. Not 1, 2, 3, 4. 1, 2, 3, yeah. So this would just be 1, 2, 3, right? Those are our only possible scenarios because 4 is not less than 4 and 0 is not a positive integer. So that's why. So what an exhaustive a proof by exhaustion is doing is noticing, look, our size is fairly small. Let's just basically try every single one. If it's always false, then we know that it's false. If we try every single one and there's a true, it will depend on the proposition. Are we proving something or something is true, or are we proving are all of them true? Then it would depend on them. But basically, we're plugging just every single thing in and looking at the results and deciding. So we have the proof by cases. The proof by cases is when you realize that basically there are certain subsections you can categorize everything into. So, for example, you might want to say when is n squared even or odd, right? So in order to do that, first, you can kind of tell, like when you square a number, if you think about it, right, there's only really 3 scenarios you can have. And let's just assume that n is some form of integer, right? N is an integer. So there's only like 3 scenarios we can have here, really. We could have, it's a negative number, it's 0, or it's a positive number, okay? Or rather, I take that back. Let me go back. For this, not negative, positive, or 0. That would be a different problem. But really what we have is it's either even, n is even, or n is odd, right? Although negative and positive and 0 is another common example, but for this problem that I just happened to write, we'd really want to be looking at even or odd. That is our only 2 options. So if we plug in like an even number, it doesn't really matter which one. We're going to see that it's 64. Now, let's say by chance though, we don't want to just prove that for one scenario. We want to prove always. Now, what's the definition of an even number? It's when you plug in something that is 2 times some other integer, it doesn't matter what, we're represented by k. So that's an even integer right there. Now, if we square 2k, we would get 4k squared, which is equal to 2k squared, which means that because we can pull out a 2 here, right, that has to be even, right? So then for odd, what would we do? Once again, we could try some odd numbers. You know, if you take like 7 times 7, you see 49 is odd. Or we could show this for everything. We could say the definition of an odd number is 2k plus 1. And we can square this, right? And then you can say, if we square this, we're going to like expand this. You're going to get 4k squared plus, let's see, so you're going to get 4k plus 1. Now, notice we can write this as 2 times 2k squared plus 2k plus 1. So now we have something that is everything multiplied by 2 and then just a plus 1. So now we know that this must be odd. Okay, so does that make sense to you guys? So that was just an example of a proof by cases, asking like prove that like n squared is even or odd, like when is it? Our 2 cases were, let's check if it's even, let's check if it's odd. So if there was a proof that says n squared is always even, well, we just showed a case there where it can actually be odd, so that would be false. So we have an existence proof. That basically just proves one, you take a random number and you prove that it exists somewhere. So what would an existence proof actually prove? Like, if you can show that one example exists, what does that prove? It proves that there are not none. So if you have some form of proposition and it says that it never exists, and you can show that one does exist, then you have disproven that proposition, okay? And then finally, we have uniqueness, which I talked about earlier, right? And it's like some really fancy words down there for what a uniqueness is. But basically, for uniqueness, you are showing that you are going to show that there are either 2 answers or there are 0 answers, in which case there cannot be a unique situation. So if you read the quote unquote definition I wrote, right? It says you find that a value exists first, and then you show that for all values, if a value exists, it equals that original value that you proved existed. It cannot be another value. But once again, in simple terms, it just means that there's only one value. That's it. Yes. What? Wait, what? Miley, say your question, then sigh.
No, I'm just like, I need that whole thing explained then.
Okay, so basically, in simpleton terms, right? If you want to prove that only one thing exists, right? That means if you can show two things exist, then no longer does only one thing exist. And if you can find a way to show that it never exists, aka you can find some contradiction or something that shows that it never exists, there are zero, then once again, you cannot have only one thing exist. If you, yes. Yes. Okay, so, that's a very interesting question. Hold up, this might take some time. So he's asking, what is the negation of the uniqueness quantifier? So the uniqueness, right, is saying that there's exactly one, right? So what that would mean is that we would basically have, we would have an or statement. We would say there is none or there is more than one. So it'd just be something like this. There is one solution. So there is an X. Or I guess it would rather be there are no solutions. Or there is a solution and there is a Y where like X is not equal to Y and it still makes it true. So like you have a function where, like you have a C of X and you have a C and a Y that are true, but X is not equal to Y. Does that make sense? Yeah. That's how you would, that's the negation of the uniqueness, yes. Yeah, so like you're trying to show like, it depends on the specific proof you're doing, right? So let's say you're proving like, for example, let's say you were saying n squared is even, right? And you were given your set of numbers is going to be 2, 4, 6. Okay, an exhaustion proof for this, like this was your entire domain. Okay, an exhaustion proof for this would literally just you be saying, okay, an exhaustion proof would be saying 2 squared is 4, 16, 36. Well, we've tried it for every single number and we see it's even. So yeah, for all n squared is even. That would be an exhaustive. You show that they're all true, but on the other hand, you could also show that maybe if we had a different universe, right? If we had like 2, 3, 4, right? Then we could have 4, 9, 16, right? And then you can show this one's false. So once again, if you have the same exact proposition for all n squared is even, and that was our universe. Now through exhaustion, you can show that they're not all even, and thus it is false. Does that make sense? Right, and like I said, it'll just depend on what you're actually trying to prove. So like, it could be asking you to prove for all, make sure it's true or false. It could be saying, prove that there's at least one, prove that there are none. It just depends. But basically an exhaustive proof is just you take your list of values, you notice that there's a limited list of values that make sense, and you just manually compute them all. Yes. Yeah, so like for that, I would probably say use a proof by cases if they don't give you like a limited number. And once again, you're gonna have to just basically have these definitions. There's a very high likelihood that something could show up on the exam where it talks about even and odd. Make sure you have the definition of an even and odd number memorized or on your sheet or something. Because if you can use those definitions, you can show for all cases or for no cases. Does that make sense? I think that's the end of the PowerPoint slide. So I am going to go ahead and I'm going to stop the recording, but I'm going to start taking questions. And I know Raj wants to talk about some Senate stuff, but I'm going to stop the recording because I don't want to take too much extra time because it takes forever to upload. So let me stop that real quick. And then I'll unmute everyone as well.